Savant syndrome, pushing the boundaries of genius.
People who have Savant syndrome possess special skills that typically revolve around music, art, memory, and math. Some historical figures who are rumored to be savants include Michelangelo and Sir Isaac Newton. These talents exhibit creativeness and rely on hard, tangible facts, which are both characteristics of the right hemisphere.
But the question is, how is it even possible for these humans to develop superhuman capabilities? To be completely honest, scientists still aren't sure. There are so many different factors in play and so many different theories. So in this video, we'll focus on Fragile X syndrome in congenital savants. Congenital savants are born with their abilities, though they might not be revealed until later in life.
In fact, congenital savants make up a majority of the savant population, but as seen throughout history, remarkable intelligence has its trade-offs. A majority of savants have autism, while the rest have other various central nervous system disorders.
ASD is more prevalent in males. We can also see this gender ratio in Fragile X syndrome and Savant syndrome.
Fragile X syndrome is the leading cause of inheritable autism. It's also a sex-linked disease, which means that boys are more heavily affected. The gene, FMR1, lives on the X chromosome where it seems fragile.
FMR1 has a region called the trinucleotide repeat, where the DNA sequence CGG repeats anywhere from 5 to 44 times. When this gene is expressed, proteins called FMRPs are produced. These proteins are thought to facilitate synapse growth and function as regulators for protein synthesis. Synapses function like bridges and they connect neurons. Neurons also have things called dendrites. They're like arms that receive messages. They also have dendritic spines to help. When the trinucleotide sequence repeats over 200 times, a full mutation occurs. This means that the crucial FMR protein is just not produced, or it just doesn't function right.
FMRP inhibits protein translation, meaning that it prevents protein synthesis. So when FMRP is gone, protein production goes into overdrive. One of the proteins that can possibly be subject to this overproduction is the SHANK3 protein. This protein acts as a layer of synapse protection. However, it's also involved in the formation and maturation of both synapses and dendritic spines. When SHANK3 is overproduced, too many new synapse connections are made, and they mature too fast. Babies normally have incredible synapse formation until they are 2 years old. Then, synapse pruning occurs and unnecessary connections are removed. This makes the brain more efficient. However, children with the FMR1 mutation don't experience the same level of synapse pruning. The FMRP isn't there to stop the overproduction of SHANK3 and other proteins, so synapse overgrowth continues.
Because synapse pruning doesn't happen until around the age of 2, symptoms of the genetic mutation won't be revealed until a child's toddler years.